Okay. Right here. So, yeah, the quiz was kind of a fiasco. It's annoying. I don't know what was going on with that. I still haven't heard back from our DE guy about what's going on with Canvas, but some people found the images weren't showing up. Did you make it? Did you get it to work? Did you try it yet here? Okay. Yeah. So that's why I sent the images, so you basically have a preview of the quiz. And Jonathan had a question about the quiz.
Yeah.
And let me see. I bet I have. I sat down last night expecting to get some grading done, and then I had to deal with this fucking problem. So this is the email in your mailbox. And question. I don't want to give too much away because I want you to think about these things, right? But go ahead.
Well, I think in the force vector,
Yeah.
it's a hat minus a hat.
Yes.
I got this answer by doing all the work just normally. And I marked it wrong, so I went back and checked it. I couldn't find what I did wrong.
Okay.
And I used a plus instead of a minus in the force vector. And it came out as the correct answer. Right.
Yeah, weird. Yeah, that looks, the way it's drawn, it looks like A plus B, doesn't it? Maybe I interpret it as a plus. Okay, well, anyway, do your best because I'll just fix that after the fact. Yeah. Yeah, so don't worry about it. Do what you think is the right answer. And then if it gets marked wrong and you actually have the right answer, then I'll fix it. So, yeah, this is these are the kind of things you should know, right? And this is one of those things that people usually forget about now, which is how to do the magnitude of a moment about a line. It's a complicated process. There's several steps involved. So go back and look that up. Look at some of those problems that we did and try that. I'd rather not do that. You know, if you want to work these as a group or something on the boards, that's fine. I just don't want to show you anymore because that doesn't really stick if I do that. So it's time for you guys to kind of dig in and find those answers. Any other issues come up for anybody? No. Okay. Then what are we going to do today? Today's review. It's a review led by you all. So there is a practice test. Did anybody not get the practice test? So this is sort of what it looks like. There are 4 questions for practice test. That's the homework assignment. And what would you like to do? Would you like to just work on them? Would you like, did you work on them and you have questions? It's really kind of open floor. Yeah. Okay, yeah, we can also go over any homework problems. So for 150 from homework 6, I'm going to get that by going to my curriculum repository, which is right there. This was actually a test question once long ago. Aziz, what was the, where were you finding difficulties? Finding the moment. Okay. So you want to share with me what part you were finding of? So the force is -40 times b. That's what you're saying, right? Yeah. So for the rectangle anyway. So this is going to be 40b, right? Mm-hmm. Yeah. Well, if you had to tell me the location of where that equivalent force is for that distributed load in terms of A and B, what would you say? It's kind of a number line thing, right? You want to know how far is that thing from point O here? How far is that 40-pound force, which is the equivalent force, well, 40 times B force, the equivalent force for that distributed load, how far is that from O? That's the moment arm, right? Why do you say that? A little over 10 feet? 10 feet is the distance to the triangular load here. All you know about that vertical load is that it has a width of B, and the left side of that vertical load is at A from O. Yeah, you got to go all the way over by A amount, and then you got to go an extra B over 2 to get to the center of that rectangle, right? Yeah. That's how you do those. You're finding the moment arm. Yeah. Good. Okay. Any other questions? This is the kind of stuff that's great, when you have this like, oh, I get it now. That's what I want to hear, because that's when you get that, then it stays. Because now if that kind of thing happens again, you're like, oh, that's not a problem. Yeah, any homework question on 3 through 6 is fair game. Or any questions on the practice test? Number 4 on the practice test. And let's see, where is that thing anyway? I think it's also in the same place. Thank you. Yeah, these are also rather complicated problems. This one is a complicated problem. It really is testing whether you got the concept down of what's going on here. This one also is a pretty complicated problem. What they're saying is that we're going to take those two distributed loads, one of them is vertical, one of them is horizontal, and we're going to replace it with a single force acting somewhere on that beam between B and C. Now, if you just sort of look at the net force, you can pretty much convince yourself that there's going to be a downward net force acting on the top, and there's going to be a leftward net force acting on the side. So if you add those two together, you're going to get some kind of a diagonal downward force, right? Downward to the left. And you can put that thing somewhere on the beam from B to C, and have it an equivalent system, right? So in other words, you could take those forces and change it, exchange it for a single force somewhere over here. And we have to tell where the resultant's line of action intersects member BC. So that resultant means you can get the same moment about C if it's sometimes it could be at different places on the, so if the net force was like going this way, you could place it here or you could place it here, and it would have the same net moment about point C. So sometimes I might ask you to put it on the horizontal part if it can actually work there. But in this case, the way the forces are pointing, the only place it's going to actually intersect the structure is on the BC beam. And so this is going to be our FR, and we have to figure out what is this distance, say little d from C. It's going to give us the same moment as those distributed load forces are doing about point C, right? It has to be an equivalent system. So that's what's being asked. Now, we've done a few of these, but how would you actually go about it? Does that answer your question, Trent, or do you want to actually see how to actually do it? Yeah. Yeah. Good. But for those who may not quite have it down, there's a lot of these problems there's a conceptual part of understanding what the question's asking, and then there's sort of a procedural part where you have to follow certain steps to get the answer, right? So for those who are maybe not seeing that yet, and this might be a good exercise for everyone to do today if we run out of questions, is just to go through each problem and write a plan of how you would solve it. Because it takes time to do all those computations. But if you have a good plan in your head, this is where you're going to start, removing yourself from the nitty-gritty, right? As an engineer, when you get a problem, you're going to start thinking in terms of plans to get the solution, not actually just start, doing cross products and vector operations and stuff, right? You want to have a good plan before you start those, because then it'll see you to the solution a lot more effectively, right? So what would be the plan, knowing this is the problem, and there's a fairly few number of steps. What would be a plan? What would be the first step of a plan? A free body diagram could do that. But the free body diagram is mainly for equilibrium problems. We're trying to find where all the forces add up to 0. This is not an equilibrium problem, is it? This is an equivalent force system problem. You could do a free body diagram, but free body diagrams, we mainly do those so we can write like the sum of the forces equals 0, the sum of the moments equals 0. And I'm not going to discourage anyone from doing a free body diagram, though, so let's put that down there. Once you have a free body diagram, what would the next step be? Find the FR for the triangular load, and so I like to just, I like kind of drawing little triangles there, so you can find, oops, the triangle's going the wrong way. You can find the net F for the triangular load, right? That's a distributed load. That's the area of that triangle, right? And you can find X, where that triangle is going to actually, where that effective force of that distributed load is going to be, right? And you can do the same thing for the rectangular load. And call that Y rectangle, where maybe this is the, I don't know where, how we're going to actually locate these things, but actually, what would be a good reference point for X triangle and Y rectangle? X relative to what? There's no XY axis on it. where should we put the origin of our XY axis? How about it's C, right? Because that's where we're going to have to find that distance relative to point C, right? So why don't we put our axis right here? All right, so then this would be our distance here. This would be X triangle, right? It would go straight below where that effective force is going to intersect the x-axis, right? That's how far that force is from the right edge, right? And that means what would y rectangle be then? How would I label that on the drawing? The height, right? The height from C, right? So this would be y rectangle right here. I mean y triangle. No, y rectangle. Sorry, get my shapes right. Okay, so what? What if you get those, and what if you label them relative to C? What are you going to do with that information? What's the next step? Find the moments, right? So find the sum of the moments at C. Okay, that's the next sort of high level step for all of those, for both of those two forces, right? And then what? What's step 5? Now we got the sum of the moments at C. What are we going to do with that information? The sum of the moment divided by the sum of the forces, and yes and no. That works when you're on a beam and all the forces are kind of vertical and they're all pointing in the same direction. In this case, the forces are kind of pointing in different directions. So we can't just add those forces, right? No, you don't just divide by y. Yeah, this is kind of where it gets tricky, right? What is it that we're trying to prove here? We're trying to prove that these are equivalent systems. Here's system 1, here's system 2. System 2 just has that single force Fr acting on it. And that Fr has a horizontal and a vertical component. In order for them to be equivalent systems, right, what has to be true is that the sum of the forces in system 1 has to equal the sum of the forces in system 2, and the sum of the moments in system 1 has to equal the sum of the moments in system 2. That's the kind of problem that we're trying to solve here. We got to get those to the equivalent system. And we just found the sum of the moments about C, and this is actually in system 1, right? Now we got to find the sum of the moments in system 2. There's one unknown in system 2, though, right? We know what is the horizontal component of Fr equal to? Well, more generally, according to our plan, in our plan here, what is the horizontal component of Fr equal to? We already figured it out. What is the horizontal component? On our plan, what are we calling it? F rectangle, right? So this is F rectangle. And then what's the vertical component of that force? F triangle, right? So this one, step 5 is going to be, all right, I'm kind of going to move this down. I think I'm going to move this down here because I'm running out of space here. Step 5 is going to be find the sum of the moments about C in system 2. And it's a single term, right? There's only one term in that moment calculation. What is it? F rectangle times D, yeah. The F triangle doesn't affect the moments. It affects the FR, but it's not actually giving us, oddly, right? It can't give us that, it can't give us a moment about C because of where we're placing it on the beam, right? But that's okay. We just make D a little bit bigger, and that will sort of account for everything that we need to, right? So that is going to equal F rectangle times D. These are all the little insights that you make along the way when you do these things, right? And it's, you know, you got to be open to this stuff. Sometimes they're gonna throw problems that are going to be a little bit unusual, stuff that, you know, because that's the only way to tell if you really got it, right? If we just give you a problem exactly like what you solved in the homework, that's just rote learning. If you give you something with a little twist, you actually have to think about what all these concepts are that we've been going over. And that's what engineers do, right? Engineers don't solve something that somebody else already solved. And then, so then step 6 is going to be, you know, solve for D. Any other questions on that one? That's a good one. You see, a lot of these questions now have a lot of stuff buried in there. You know, they're multiple steps kind of thing, multiple concepts involved. Any questions on another problem you want to look at?
Can you go over number 2 for the assembly?
Sure. Mm-hmm. In order to raise a lamppost, force F is applied to the cable. F is 200 pounds. Determine the moment produced by F about point A. So this is, again, what's the, you know, what are we trying to find here? The moment of F about point A, right? The moment of, you know, so we're finding yeah, this has quite a few pieces to it as well, right? It's not just you know, just cranking through some stuff. What do we got to do here? What do you see that needs to be done? What do we got to figure out before we can do anything? Finding the moment arm with F. And let's, sometimes the plan can be, initially it can be kind of like brainstorming, right? So some of the thoughts are, we got to find the moment arm for F. What else comes to mind? Find angles at B or C. What else comes to mind? Brainstorming. Throw out some ideas. No, no, don't bring in the law of cosines. No, go away. If you like the law of cosines, you can use that. But I removed the law of cosines. I used to bring in law of cosines in like chapter 2. They have a section on there on how to use that, but it's so annoyingly obtuse when you could just use Cartesian vectors and stuff. No, there's something really important that no one said yet. We got to do first. What do we got to do? Sorry? Position vector, right? What position vector? Yeah, you got to find R, B, C. Then what? Yeah, unit vector, UBC. And from there, that will give you Cartesian vector for F, right? You need that. I mean, you can do this using scalar stuff, but having the X and the Y components for F, pretty helpful, right? And you'll get that from these steps, right? That's what we learned these things for. This gives you, when you see like a force oriented along some geometrical cable, usually, or an arm or something, and it's just telling you the magnitude of the force. You got to start putting points on there to turn it into a unit vector, which will encode the direction of that force for you. You could do the angles, like Dylan said. You can easily do it that way, yeah, and that's totally fine to try to figure out the angles of that triangle. Law of cosines, law of sines will do that for you. But we never showed you that. We didn't really emphasize that in chapter 2. We emphasize position vectors and doing it this way. I think it's a little more general purpose, gets you out of a lot of hassles a lot easier than doing that trig stuff. Yeah. Okay, so that would be one step. What else could we do? Suppose we got F. Now we got F. We know what Fx is. We know what Fy is. What are we going to do to find the moment of that force about A? And remember, when we're doing moments, even with 3D moments, you can do the moments using like 2D or 3D. You can do vector analysis or scalar analysis, right? So you can decide, and maybe we can do since we have F as a vector, we can call this, X, Y, and, the Z-axis could be coming up out of the page. Let's put the Y up here, sorry. If we're going to do scalar moments, how would we solve this with scalar moments? The moment of that force about point whatever, about A. Corey, what are you thinking? Find the length of BC. Well, you would find the length of BC as part of finding UBC, because UBC is going to be RBC over the magnitude. But that's not going to give you the moment. Let's assume that we got that already. And all that gave us is a Cartesian form for F. A lot of people are quiet. Why don't you want to like just chat with your neighbor for a little bit on how you would do the next step? Because I'm not hearing an answer. I want to make sure people have a feeling for how this. If you're all stumped, my guess is probably a lot of people have it, but they don't want to say it for some reason. Why don't you have a little discussion in case you don't have it, and then maybe you can help educate the person sitting next to you, and then we'll come back. Don't tell them. I know, but don't tell them. Don't go that way. Unless Corey is a trig geek, don't do that.
Well, you have 75 degrees, 29 degrees.
Anyone have any thoughts? Joel, anything? Are you stumped? Okay, Alex, any thoughts? Thanks, Dylan. Throw out everything we learned in statics and go to law of sines. Yeah. We have so many tools in statics that we learn and make it real easy. For instance, you know how moments work. What's the definition of a moment using vector notation? M equals what? R cross F. If you've got F as a vector, and this only works, by the way, it has to be 3D, doesn't it? So you might have just had a two-dimensional F here, but you got to have to add a third component for F, which is going to be 0. The Z component of F is going to be 0, right? So in other words, F is going to equal some Fx Fy and 0. Or whatever notation you like, fxi plus fyj plus 0k. And what's R going to be? Well, RAB, or more easily, yeah, AC, even more easy, right? So R could be RAB, in which case you got to do a little trig there, right? You know, 20 times the cosine of 75i plus 20 times the sine of 75j, right? Plus 0k again, right? And or it could be R AC. Remember the law, what is that? The principle of transmissibility says that that force is going to have the same moment. You do the moment arm AB, do the moment arm AC, those are going to give you the same answer. And that is just that cross product. Which is a determinant, and yeah, maybe the law of sines is going to be a little less intimidating. If you don't like those kind of operations, it's easy to mess up a determinant, you know. Okay, but that is a viable way to go, and it didn't require any trig except the trig needed to find the x and y for point B. If you're going to use point B, because you don't even have to, you could just use point C, and that would be real easy. So, so that's one way. Now, the other thing is, if we're going to use scalar moments, how would we use it? Do it using scalar moments. RF sine of theta. I'm thinking more like again, we didn't really have to do that. Yeah, you could if you knew what theta. You know, you could do all that stuff. RF sine of theta. Yeah, but we did this also with the principle of moments. The principle of moments says that basically, you know, if you have if you can break your force into sum of forces, then the total moment is the sum of the moments of each of those components, right? The principle of moments, that's a Led Zeppelin album. Go look it up, play it tonight if you want. The principle of moments says you take a force and, you know, like this force here, and there's, so the principle of transmissibility says you can apply this force right here, right? That's the easiest place to do the moment about A, because then you don't have to worry about the horizontal component of that force, and you just have a single moment arm there, right? The principle of moments says, the principle of transmissibility says you can put that F here, you can put that F here, if that works for you. But common sense says the easiest place to do that moment calculation is going to be if you stick it right at C. And that F is going to have an Fx and an Fy. And you already figured out those terms right here when you found Cartesian F. Okay, and so what is a scalar moment? Fy times 10. And see, if you don't know the principle of transmissibility, if you don't know the principle of moments, then you can't do this stuff, right? That's why those concepts are pretty important. You go off in some trig nightmare. Some of you, you know, some of you are maybe know just enough trig to get yourself in serious trouble, right? But if you know the concepts, then you just go, oh yeah, it's real simple. Right, so it's just Fy times 10. Drawing pictures, very helpful. It's not a free body diagram, but it's a help. Any kind of sketch like that, when you start kind of doodling like that, that can really help open up the problem solving process. Problems look really hard. You know, that problem looks really hard when you first look at it. A tipped over light pole, first of all, you're worried about it going to crash on somebody's head, you know, but really that's a distraction. It's really just finding the moment of that force. Somewhere along its line of action, you can put that in, find a moment arm, real easy. The principle of moments, right? Principle of moments says break that thing up into horizontal and vertical components, and then the moment arms are really simple. Okay, got 10 more minutes. What would be helpful? Any homework problems? Any test questions? Want to just do a plan for another problem? Maybe problem 3 or something on together? Do a plan for 3? Sure. Why don't you maybe spend a couple minutes and chat with somebody nearby you for a plan for 3, and then we'll come together.
Across the 2 forces with the moment arm and some yes. So you do the moment arm across the F1 and you are across the
All right, so what do y'all think? Plan for this one. Yeah, you could save some time by adding. That's the opposite of the principle of moments, right? You can, in reverse, instead of having 2 forces and doing 2 separate moments, adding the moments together, why don't you just add the forces together first and then do the single moment? Yeah. That only works because the two forces are attached to the same point. Step 2. Well, you want to find ROA, right? And step 3 is going to be MO equals R cross F. Yep. Okay. And 6 more minutes. The first one, this one, this one is an equilibrium problem. So you should probably start off with this one with what? Yeah, free body diagram. Well, of what? Point B, the only point, it's a concurrent system, right? You're just going to free body diagram. All the forces are acting on point B. What are they? TBA, TBC, and FBD, FDB, which is 3.5 kilo. There is a problem still we have to kind of resolve here. What do we have to add to this diagram before we can write the equations of equilibrium? What do we got to do? Angles would be helpful. Triangles, angles, right? We're going to figure out what angle this is. We can't really write those unless we know what those angles are, right? So, you know, that is a question. And I guess I wish I had made that bigger now. Let me move this away a little bit. And it looks like it's not exactly a, it's definitely not an equilateral triangle. So what would this angle theta be, or this angle phi be? That could be part of your free body diagram. Find theta and phi. Yeah, let's not go into that. That's something you could kind of noodle through. But then suppose you found theta and phi, what would you then do? Sum of fx equals 0, sum of fy equals 0. And please write those on your solutions so I can kind of see what your thought process is. Don't just write the equations, right? Sum fx equals 0, and then continue that. And then basically solve, right? Solve for the two unknowns, basically. There's only two unknowns there. For TBC, sorry, oops, TBA. TA and TBC. So those are the plans, and if you haven't done it yet, you could sit down and execute those plans, and then check your answers. The solutions are available on Canvas if you go to the test 3 link. Test 2 link. Sorry, I'm getting ahead of myself. If you, yeah, sure. 1 second. If you go to the test 2 link, this is the practice test, and these are the solutions. Yep. Question?
Yeah, I just want to look at problem 4-11 from the homework.
4-11 from today's homework?
It was from
Homework 6?
This, I think it was 5. It's the homework with the mobile one. Yeah, it's 4. It's 4.
Assignment 4?
Yeah.
And which problem? It's not on this list here.
Oh, okay. Maybe I just didn't.
No, it's on homework 5.
I just want to compare that one with the on the practice test that we just looked at to compare why we crossed this on with ROA for problem 4-11. And for this one, we did ROA, but it's like we're making the vector to the point where the force is acting. For this one, we didn't do it to ROB. We didn't use ROB and cross it with the force.
So you're comparing this with the practice test problem. Which problem on the practice test? 3? This one?
Yeah, so I'm thinking for
this one there. On problem 3, we crossed it with ROA. And on this one,
I believe we crossed it.
No, I wouldn't recommend crossing F with ROA. That wouldn't give you the right answer. When you do a moment calculation, the moment arm has to connect to the to the point about which you're doing it to some line of action of the force, right? So for this one, the plan would be, you do have a choice here. But it's basically, so MO is going to equal, R cross F, but you have a couple choices here. You could do R OB, or you could do what? ROC. Now there is a variant of this one where you have to find the moment of the force about the OA axis maybe. And then, if you're trying to do that, then, you got to find ROA, turn that into UOA, right? And then you got to find like maybe this ROB here or ROC. Yeah, that is a little more complicated, but this is a simple one. We actually did this one in lecture.
Yeah.
Okay. You mean in your solution? Okay. Okay, see you tomorrow. Yeah, we did that during lecture, yeah. Hey, I'll take your homework 7. Wait a second. Let me pull that up again. I think I saved that one. So, I'm sorry, your question was?
Because we only use the horizontal.
You only use the horizontal, yeah.
Yeah. So we know
I'm not registering what you're saying.
like because I was confused about this because I was like a 2/4.
Yes. Yes.
Getting the south.
Right.
So and then you had said that we're only talking about horizontal one. That's the only one that matters.
If you apply the force on the beam BC, that's the only one that's going to matter.
Yeah.
Neglecting the thickness of the beam. But if you applied it, like if this was an L shape that or a C shaped beam that had a bottom there on the x-axis, and I don't know if I can draw this. Actually, I could. I'll just snip it again. So you know this thing is acting this way, but what if this was actually a C-shaped thing, and they told you, where to put this force on the horizontal? Let's call this E. If this is maybe C, this is D on the CD beam.
Yeah.
And how far from C would that have to be? Well, now the only component that's going to matter is what? The vertical component. Because the horizontal component isn't going to give you a moment about C.
Yeah. So we would only take the moment, the force component.
Yeah, the force component that's going to actually give you the moment is how you do that. Because you have to have equivalent systems, right? You got to have the same moment about forward.
Yeah.
Yeah. Definitely a lot of subtleties here. Thank you.